Alright, so covalent bonding. Recall ionic bonding is where electrons are fully given up. Covalent bonding is where electrons will be shared. So recall what a chemical bond is. A bond is an attractive force between atoms or ions in a compound and depend on the electron configuration. Involves valence electrons, the electronegativity. And why do elements bond? To achieve a stable electron configuration. They follow the octet rule. Atoms lose, gain, or share electrons to achieve a stable configuration of 8 valence electrons, with the exception of helium and hydrogen only needing 2. A stable electron configuration is really just a fancy way of saying lowest possible energy state. Everything wants to be in the lowest possible energy state, and that's the reason why things bond and come together. So, ionic properties, they exhibit a crystal structure. They exist as solids. Again, these are usually the properties of ionic bonds. It's not true for everyone, but usually they exhibit crystal structure, exist as solids. They dissolve easily in water. They have high melting and boiling points. They conduct electricity when dissolved in water. And they have high electronegativity differences. And now let's begin with covalent compound properties. Usually they have low melting points and low boiling points. They usually do not dissolve easily in water. They do not conduct electricity in solutions. They exist as gases, liquids, and solids. And they have a low electronegativity differences. Again, this is not true for everyone. For example, sugar is covalent, but sugar can dissolve in water quite easily. But if we compare it to salt, there's a lot more salt that can dissolve in water than sugar can dissolve. But usually they don't dissolve in water easily. They do not conduct electricity in solutions. Again, there's always exceptions. But if we compare the melting point of salt versus the melting point of sugar, you can actually caramelize sugar and melt it quite easily. Whereas salt, you could put a regular lighter up to it and it would never melt it. So some common covalent compounds. Nitrous oxide, which I'm realizing is named incorrectly. Let's look. Nitrous. I don't actually have a correct periodic table. I need to print off a humongous supply and throw away my old ones. Where do I have? It was at the end of the last test. So nitrogen has a 3.04. Oxygen has a 3.44. So it is most definitely, that's a difference of 0.4. So most definitely it's covalent. But the name of it is wrong. It should be nitrous monoxide. I know why it's named that way. It's named because that's the common name of it. Like, for example, methane, which is carbon tetrahydrogen, we just call it methane. So nitrous oxide is the laughing gas used as an anesthetic and to boost auto engine performance. Methane is flammable gas used in fuel and homes for domestic heating. This is your natural gas you get at your house. Sugars like sucrose and glucose are used in food and energy production. Hydrogen peroxide is used as a bleaching agent uh, and other things. Carbon dioxide. Carbon dioxide is the most common example of a covalent bond. It's a gas used by plants during photosynthesis, produced in respiration. Water is also a very common covalent compound. Water and carbon dioxide are the two most studied elements that we'll look at for covalent bonds. So a covalent bond occurs when valence electrons are shared between atoms, usually between non-metallic elements. Covalent bonded compounds known as a molecule. So whenever covalently bonded compound known as a molecule, these shared electrons are part of the valences of all the atoms involved. They satisfy the octet rule. Since electrons are shared, no charges appear. Many combinations can occur between two nonmetals. For example, carbon and oxygen can form carbon monoxide, or they can form carbon dioxide. So, if I ask you what happens when you mix carbon and oxygen, well, they could either make carbon monoxide, carbon dioxide, or any other combination. Because of the low electronegativity between the two, usually they won't react unless you force them to react. Your pencil and diamond are made out of pure carbon. There's about 20% oxygen in the air. They're not constantly turning into carbon monoxide or carbon dioxide. So usually you have to add a little energy for them to react together and make those elements. So if we look at, let's say, carbon dioxide, we usually always put carbon in the middle. Carbon has 4 valence electrons. And we have oxygen on one side of it. And another oxygen is going to be on the other side. Recall that each atom wants 8 valence electrons. So if we can see, oxygen is missing 2, and carbon is missing 4. We can see that we can pair these up right here. If we were to move this around a little bit and pair these up so that these 4 electrons are 2 electrons from carbon is shared with oxygen, and 2 electrons from oxygen is shared with the carbon, make these shared. And likewise over here for this oxygen. So this this carbon, or this electron's going to go here. This electron's going to go here. This one is going to go here. And this one goes over here, sharing. Same thing for this. When we share them like this, we now see this oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons. This carbon now has 8 electrons. And this oxygen has 8 electrons. And usually what we do when doing Lewis dot is if we have an electron pair bond, we can represent with a single line. So, and we usually make the lone pairs fancy. R. It really doesn't matter how you draw the remaining ones that are left off. But this would be the chemical structure for CO2. This is how you write the formula. So it's a double bond between carbon and oxygen. And the oxygen has each oxygen has 2 lone pairs. So each line represents 2 electrons that are being shared between the carbon. So let's look at CO. Try working it out by yourself. What do you think the final formula is going to look like? So what y'all end up with? Are y'all still working on it? Alright, so we got carbon. And we got oxygen. So, oxygen only needs 2 electrons for it to complete its octet roll. So I'm going to go ahead and share those 2 electrons. So carbon is going to share 2 electrons. With the oxygen. And oxygen can go ahead and, so carbon needs 4, oxygen needs 2. I'm going to go ahead and share 2 electrons with the carbon. So I'll move these over. Now I got these 2 right here. Right? So let's look at the octet roll so far. This carbon only has 6 electrons. This oxygen has 8. So in order, again, every atom needs to have a total of 8. So what I'm going to do is, again, so what do you think the next step would be? Oxygen is going to give over 2 electrons here. So here we have 8. Here we have 8. Octet rule satisfied. And every 2 electrons being shared, we can replace with a straight line. So it's triple bonded. We call these straight lines a bond, by the way. Anyone get that? So why I presented it is this challenging, or that was a challenging one. Let's look at another one. Let's try N2O. Try working on it by yourself. Mm-mm. Count how many around it. So every line represents 2. So you have 8 around this nitrogen. You have 8 around here. So, but you have, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have 12 around the oxygen. So if you're trying this out, I should have gave you a hint. Nitrogen is going to be your center. So nitrogen, nitrogen, and oxygen. Over here. Because if you're working it out, you'll find it's impossible, I think, to do it with oxygen as the center. Because you keep giving oxygen way too many electrons. I had like 12. Yep. See, this shows you that the structure actually depends on science. Anyone get it? I gave you an easy one. This one has 3 correct answers. This is a resonating one. It actually resonates and changes its electron structure as it oscillates between 3 possible states. Most of them only have 1 correct answer. Alright. So I'm going to do the most straightforward first. So let's begin with nitrogen and oxygen. So oxygen needs 2. Nitrogen needs 3.
Did you have water leak?
One of my desks are missing and there was a lot of work.
Is that? They said there was 2 ceiling tiles in them.
That's been there.
Pop off your feet outside the classroom.
That's been there for a while.
It's been here for a while.
Yeah.
Not coming back though, getting dark again, anything.
They said that there was 2.
That's been there too.
They said there was 2 ceiling tiles that was down. Let me go find this thing.
Alright, so I'm just going to give up 2 of the electrons to the oxygen. So, right there. And I'm going to return 2 oxygens back. Like this. So that gives me 2 electrons right here. So basically, I'm moving these 2 dots over to the right, and I'm moving these 2 dots over to the left. Does that make sense? So that means there'll be 2 here, so 1, 2, 3, 4, and there'll be 1 right there. I like to also go ahead and replace dots with lines to make it easier. I'll do that later. So I can now link these 2 up. And then let's check to see the count on all of them. And I can pair these off too. And move these down here and group these together. So 1, 2, 3, 4, 5, 6. 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So looking at it, this has 6, this has 8, and this one has 8. So what nitrogen's going to do is freely give away our share. It's, yeah. Like that. And now we can replace everything with lines.
That's how mine came out.
This is not the only solution, but this is the most straightforward to get. By the way, it really helps, at least teaching this, if I color code it. So you can keep track of the initial 5. But let me show you a quick way of doing this. So I'm going to redo this.
Miss Bambi, if you're on campus, at the front office, Miss Bambi.
How I personally do it is I initially guess and be really quick and sloppy. And then usually I'll restart when I get it wrong. So I know I can immediately group these together. I can immediately group these together. Oxygen just needs 1. So I can group these together like that. And I'm going to guess that this is temporarily the solution. And I can group these two together because they're on opposite sides, like that. And then I double check to see if I'm right. So I find, so when I have nitrogen right here, like this, and I have oxygen like this, like here, what I can do is if I'm missing one right here and missing one right here, I can link these together by a line. If I'm missing a dot right here and missing a dot right here, I can group these together and place it like that. Does that make sense? And now I double check to see how many I got around it. So 1, 2, 3, 4. A line counts as 2. This would be 6. 1, 2, 3, 4, 5, 6, 7, 8. 8. 1, 2, 3, 4, 5, 6, 7, 8. So this one is missing 2, so I can give these up. Let's look at the other structure we could have got. So nitrogen, again, starting with 5. I personally know that nitrogen likes to be the most stable configuration is a triple bond of the nitrogen. And I would assume that it's going to try to gain a triple bond. So let me do that. So I'm going to take this one and this one, this one and this one, and this one and this one, and go ahead and triple bond it. So nitrogen, triple bond with this nitrogen, and the oxygen I have not done anything with. Does everyone get what I've done so far? Basically, these two shared, these two shared, and these two shared. So check, this is 6, 7, 8, this is 8. 6 plus 2 is 8. 6, again, I'm not sharing anything, but it needs 2. So what do you think I'm going to do? I'm going to take these 2 electrons and share them with the oxygen. So I get this formula. That's a valid solution. And let's do the same thing. So nitrogen. You'll see why I taught y'all earlier of spacing these out. It makes it, if you draw it like this to begin with, it makes it easier. It's just on the final thing, we group all the electrons as pairs. So when we write it as a single atom, the Lewis dot, we spread these out as much as possible. But on our final compound, we always group 2 electrons as pairs. So another possibility is let's fill up the, let's try to get a triple bond on the oxygen. Actually, how do you get that? Alright, so I'm going to group these together. So nitrogen, and that's 1 there. So it's missing 3. I'm going to give it 1 here. I don't even know how to do that. That one's confusing to even me. I know that what happens is in this structure, the electrons are constantly moving between each atom. It's constantly, the electrons being shared are not staying on being shared between only two atoms. They're constantly bouncing back and forth. Like the nitrogen being shared with this nitrogen will occasionally be shared with this oxygen, or come over here, and what happens is they're constantly resonating. They're constantly going back and forth in this, doing all these three. So that's 6 plus 8, 6 plus 2. I mean, it's really. Let's see, so. I only need one bond over here. How do I get one electron? I'm assuming this is an intermediate state. That some of the electrons from the oxygen is moved over. So 1, 2, 3, 4, 5, 6. Add the 2 electrons. Now that'll be a double bond. I don't understand how they get this one. It's weird. I'm not going to give y'all anything this complicated to where this situations. I'm thinking some of the oxygen electrons have jumped over to the nitrogen. Let's try this one. And nitrogen monoxide. And also methane. Methane is super easy. For the heck of it, water. Alright. So nitrogen. Oxygen. So again, we can see these two easily connected. These two easily connected. So we can create a double bond like this. which leaves one electron left. Actually told you all wrong. This should have been Na negative. If we throw away this electron, it becomes N double A. It becomes an ion. I forgot that this is technically an ion. So remove an electron. Carbon is very easy. Hydrogen. So I'll just come over here and fill this gap. So, hydrogen, remember, the exception to the octet rule, it only needs 2. So the formula for methane looks like this. And water, something similar. I think I only have a minute. Less. But a little preview of why this is important is we're also going to be you'll need to be able to tell me what the shape of the atom is. The 3-dimensional shape of an atom. Is it tetrahedral, trigonal, pyramidal? Based on the chemical formula. Basically, you have to draw out the electron pairs and realize how much they push away, but we'll get into that later on. No. You should, before you enter a building, kick your feet off and...
Not just for me.